So we continue with the introductory aspect of molecular spectroscopy. In the last video, we started talking about intensities of spectral lines, which is related to the height. So I've corrected this here. And we said that the intensity is dependent on the population, that is the amount of a substance or amount of molecules present in the initial state of transition, and that's dependent on the degeneracy of the state, the energy of the state, and the temperature at which the experiment or the transition is being carried out. So today we continue, or in this video, we continue with the concentration or path length of the sample. So that should actually be the concentration and path length of the sample. In an experiment, there's a cuvette which holds the sample. Light is passed through in, and then some part of the light is absorbed, and then we observe the light that comes out of the sample. The concentration talks about the amount of substance present in the sample, and then the path length deals with the dimension of the cuvette. If we look at it, the fraction of light that usually goes in, the amount of light that goes in is different from the amount of light that comes out, usually. Not always, but usually. That's because the sample must have absorbed some substance. Now, the fraction of the incident light, that's the ratio of the outcoming light and the to that of the intensity of the incoming light, that ratio is called transmittance. It is usually less than 1, and if we multiply it by 100, it becomes the percentage transmittance. The amount of light absorbed is related to the transmitter's T by a logarithmic equation. So A, that's the amount of light absorbed by the sample, is equal to minus log of the transmittance, where the transmittance is the ratio of the fraction of the incident light that passes through the sample. It's frequency dependent. So the amount of light that passes at a certain frequency is different from the amount of light that passes through another frequency. And this is also dependent on the energy level. According to Beer-Lambert, how does this affect the intensity, the concentration, and path length? According to Beer-Lambert's law, if you pass light through a sample, the absorbance is directly proportional to the concentration, that's the amount of substance present, and also proportional to the path length, that is the distance traveled by the light. So the more the concentration, the more the light that is absorbed, the longer the distance traveled by the light in the sample. That is, so we're looking at the cuvette now. The bigger the cuvette, then the higher the absorbance. So the proportionality constant is the molar extinction coefficient, or the absorptivity coefficient. The molar extinction coefficient is a old terminology that is still in use. So we can relate absorbance given with this equation to the absorbance in relation to transmittance, and we can relate the fraction of light, or the amount of light that is passed out, to the incident light using that equation. So that's the other one that affects the intensity. So the intensity increases. So according to this, if we're measuring the light absorbed, the intensity will increase with concentration. The intensity will also increase with the path length. There is an example in your notes. There's a calculation example in your notes. A water solution of colored compound has a molar extinction coefficient. So that's our proportionality constant E. So the proportionality constant, I did not mention that the other time, is also dependent on the wavelength. So it has a molar extinction coefficient at this wavelength. We're to calculate the absorbance. So we know that absorbance is ECL, which can easily be calculated given the concentration 3.4 times 10 molar concentration in a 1 centimeter cell. So this is given in centimeters, so we can retain in per centimeters. We can retain this unit rather than converting it to the SI unit. So that's the absorbance. There's a relationship between absorbance and transmittance, and we can obtain the transmittance, and the percent transmittance will be multiplied by 100. That's 8.1%. The last thing that affects the intensity are the selection rules. Selection rules or transition rules, they are quantum mechanical in nature. So it's a rule that determines whether a transition is allowed or not in a certain frame. So when what we mean by in a certain frame is that the selection rule that applies in vibrational spectroscopy may not necessarily be the selection rule that applies within rotational spectroscopy. Over the years, quantum chemists have tried, with mathematicians and physicists, they have tried to represent many things in equation and have come out with several things. One of them is the quantum numbers that we observe with hydrogen atoms. The N, S, that's the principal quantum number, the orbital quantum number, and all those quantum numbers. They are a result of mathematical calculations and not just pure speculations. So a selection rule, it's a quantum mechanical rule that determines whether a transition is allowed or not. So how does this affect intensities? If the transition is allowed, then it is intense. If it is not allowed, in which case we say a forbidden transition, then it will either not occur, or if it occurs, it has low probabilities. So for example, a molecule must be polar for you to observe it in rotational spectrum. So if it's not polar, you would hardly observe any rotation. So each transition, according to the selection rule, is related to the dipole moment present in the molecular state energy level and the two different states from which a transition is occurring. So a transition is occurring from state represented by psi1 to a state represented by psi2. Now, the transition dipole moment connects the two together. If this is 0, no transition is allowed, or if it is very low, you have transition of low intensity. Now, if it's closer to 1, then if it's non-zero, then the transition is allowed, and then you have an intense observation. Now, the thing about this is that this equation leads to the different selection rules that we have with various quantum numbers. There are two types of selection rules. There's the gross selection rule or the general selection rule, and then we have the specific selection rule. Now the gross selection rule is related to the properties of the molecule. For example, like I just mentioned, if you have to observe a molecule to go undergoing a rotation in the microwave region, the molecule must have a permanent dipole, which means the molecule must be polar. If it's in for molecular vibration in the infrared region, the molecule has to change its dipole moment with vibration. If it's rotation with Raman, the molecule does not have to be polar. The specifics, there's a video that we can see. Now this simulation has been provided by University of Colorado, so you can actually go online and check this out on your own. I may be able to provide the link somewhere, or you can just Google it, simulations FET Colorado. So this is microwave region. You can decide to choose anyone. So I just mentioned that you can, if your molecule is not polar, it will not undergo rotation. So that molecule has absorbed energy enough for it to rotate, and it rotates. When it doesn't absorb enough energy to rotate, if we change it to water, water is also polar, it rotates. But if you change it to oxygen, it does not absorb microwave light, so it will not rotate. If we try it with infrared, now there should be a dipole moment change. There's no dipole moment change, but with water molecule you will observe some vibration. Okay, so that ends our discussion on intensities of transition lines and what affects them. In the next video we will be looking at spectral line width, and in this video we will end our introductory class.